So we are a dynamic, customized software training platform dedicated to offering a diverse array of software training programs. So each session is carefully tailored to meet the unique needs of our participants. So whether through personalized one-on-one training or specialized courses designed specially for you. So on today's webinar is a part of our promotional series for VectorETech. So to ensure you never miss out on such fantastic opportunities, please connect with us on LinkedIn, Instagram, and Facebook. Follow our pages to stay updated on our latest products and services, so which we frequently showcase on these platforms. So these platforms are also your go-to resources for communicating directly with us for more information. And also, so are you an expert in a particular tool or a programming language? So we would be thrilled to welcome you to our team as a faculty member. So join us in our mission to spread knowledge and empower the community through education. And additionally, if you are looking to advance your career in data engineering or transition into this exciting world, so we offer a comprehensive master training program tailored specially to the needs of the data engineering professionals. And so in this master training program, so we are going to cover a very good number of topics, so which we call it as a 360 degrees comprehensive curricula. So wherein we deep dive into dimensional modeling, Azure Data Factory, Azure SQL Data Warehouse, Snowflake, DBT Cloud, Azure Databricks, Azure Key Vault, Power BI. So wherein we cover every other aspect of the data engineering, and we not only teach, so we also go through multiple real world projects and scenarios, use cases. So our this entire training program will be like 4.5 months, and we'll be offering that for 30K. And if you are like paying it in a single payment, so we offer a 5K of a discount. So that means you will get this entire program for 25,000. And if you are wish to like do part payments, like if you want to do two payments within a month, so we also allow that 15,000 per one time. And yeah, so if you are interested in this, so please do let us know. Please ping in the group, and we'll be sharing some form. So if you are interested, please fill out your details so that we can reach out to you and we'll discuss more over the call. Okay. And now coming to our today's webinar session, so that will be taken by Mr. Upendra Sharma. So we are thrilled to introduce Upendra Sharma as a key trainer in our data engineering master training program, and also will be taking this particular webinar. And as a senior data engineer, Upendra brings a wealth of experience and deep expertise in pivotal technologies such as Databricks, PySpark, Azure Data Factory, and Azure Data Warehouse. So Upendra's technical proficiency in handling large-scale data operations is complemented by his practical knowledge in deploying these technologies to solve complex business problems. He has been an instrumental in architecting and optimizing data pipelines that are not only efficient but also scalable, ensuring that organization can manage and extract value from their data assets effectively. So in his role as a trainer, Swopendra is committed to sharing his knowledge and experience with aspiring data engineers. His teaching methodology focuses on hands-on learning, encouraging participants to work directly with the tools and technologies that are shaping the future of data engineers. Through real-world examples, best practices, and interactive sessions, he guides participants from foundational concepts to advanced implementations. So please join me in welcoming Upendra Sharma with his expert guidance. Participants in our program will gain invaluable skills and insights that empower them to drive innovation and achieve excellence in their careers in data engineering. Let's explore the transformative power of data together under the guidance of one of the industry's foremost experts. Yeah, handing it over to you, Upendra. Please continue.
Hey, hi all. Hi team. Thanks for the wonderful introduction. I welcome you all today in this session. So it's good to see so many folks joining us. So a little about me. I'm a senior data engineer in one of the leading media measurement companies called GFK. So regarding my experience, I have worked with various industries like banking, food industry. Currently, I'm working with the media industry as well. So, as a data engineer, I like really like to work as a data engineer because we are basically swamped with all kind of data around us, and it's really fascinating. It's really exciting that what kind of data will be working in an organization and what kind of data will be dealing with. So it's a very fascinating job. So yeah, that's about that. About my technical proficiencies, I've been working with Azure Databricks, mainly focusing on Azure Cloud, along with some exposure to AWS as well. Uh, Apart from this, I've been dealing with the PySpark, Spark internal, Spark optimization, and also today's topic is also related to this only. So I'll be taking few Spark optimization techniques, which we should be aware about as a data engineer. Okay. So can I share my screen? If okay, thanks. So I'll just share my entire screen. Yeah, my screen is visible, right? Can anyone confirm, please?
Yeah, Upendra, it's visible.
Yeah, thank you. Thanks a lot. Wonderful. Okay, so today we'll be covering one of the most important data optimization techniques in Spark. So as we all know that Spark is a distributed data processing engine, right? So it basically processes our data, uh, uh, something called as in-memory mechanism. It takes the data, to the part of the data, distribute the data into some smaller chunks or parts, and then it processes data. So while doing or while processing our data on Spark, there are few challenges which we may encounter on our day-to-day tasks while working. So today I'll be talking about, sorry for that. So today I'll be talking about one of the most commonly faced challenge, which is called data skewness. So let me just data skewness, right? Let me just zoom it in. Yeah, perfect. So data skewness basically is a situation. So while dealing with data, as I mentioned, that Spark is a distributed data processing engine, which distributes data into smaller chunks and then it processes that data. So when this data is broken down into smaller chunks, there might be cases where data is unevenly distributed between each partition. So let's say we have 5 partitions of a particular data, and one of the partition is larger than the other partitions. So eventually what Spark will do, it will take more time to process that particular partition, which is much greater in size, leading to data skewness. So in simple words, this is what data skewness is. So uneven distribution of data across partitions in Spark, right? So this is what data skewness is. Now, how do we find out that okay, I am facing data skewness in my job, or how do I go about investigating it that I am encountering this particular problem? Because first we need to identify that what kind of problem I am encountering. If we are able to identify, if we are able to investigate the root cause of the problem, then only we can begin about rectifying the problem or thinking about a solution, that how do I optimize my data pipelines, how do I make them faster. So first we need to identify the root cause for this problem. So I have collected few images. Yeah. So in this particular image, as we can see that we have 200 jobs running, right? We have total 200 jobs running in our Spark. So it means that the whole data was divided into 200 different partitions. Here, as we can see at 12 minutes, when we first watched, 199 jobs were completed and only one job was remaining, right? After another 12 minutes, like in total 24 minutes since the job was started, we see that still 199 jobs are completed and one job which was running previously, it is still running. After 1.5 hours, after almost 90 minutes, we see that the job was completed. But as we can see over here, the 199 jobs were completed in just under 12 minutes. But the last job, only one job, took us like around 1 hour, to be exact, 1 hour 18 minutes, right? 1 hour 18 minutes it took us to complete just one job. So this is clearly a situation where data skewness is there because one partition took way more time than the other jobs. So the problem over here is that when one job takes a lot of time, so if this job was completed over here only, or let's say after 15 minutes, or let's say after 20 minutes, if this one job was completed, then we would have got our output, right? But this job, the only one job, took us more than 1 hour to complete. So our result got delayed by 1 hour. So this is basically what the problems will arise when we have data skewness. Another way which we can identify that we are having data skewness is using Spark UI. So how to use Spark UI and how to investigate, maybe we can cover in later on sessions. But for now, Spark provides us a very simple UI where we can see that what jobs are running and we can see that how much time basically one particular job is taking. So as we can see over here, this one job. So this is the time axis. So here we can see that this particular job, which is highlighted by red color, took more time than the other jobs to complete. So as a result of this, all the jobs have to wait for this job to finish. Only then we can aggregate our result. So initially what happens, our data gets broken into smaller parts. Once this data is broken down into smaller chunks, they get processed separately. Once they are processed separately, they are then again aggregated to give us the final resultant output. But in this case, all these outputs have to wait for this particular partition to get completed. Only then they can be aggregated together and we'll be having our resulted output. So this is the problem which we face when our data is skewed. So I hope that data skewness is pretty much clear to all. Here is one more illustration. So here we can see this is our data, right? Now this data is broken down into 5 smaller partitions, 5 smaller chunks. Here we can see that P3 is significantly larger than the other partitions. So as I mentioned, now it is very much obvious that this P3 partition will be taking much more time than other partitions like P1, P2, P4, P5. They will be getting completed first, but they will have to wait for this P3 partition to get processed, to get completed. Only then they can again aggregate their data and give us the resultant output. Now, basically Spark works on a master slave architecture. So Spark has its own architecture that also maybe we can cover in some basic class, but this class is related to optimization techniques. So I guess we are well versed with the Spark architecture. So Spark basically works on a master slave architecture in which there is a master node, and connected to master nodes, there are some worker nodes. These worker nodes have some memory, they have some cores which are responsible for actually processing our data, right? So let's take example of this particular executor. So this is one of the executor from, like, there could be n number of executors. So let's break into one of the executor. Now, how this executor actually works is that this executor has certain number of cores. Now, how many cores we can define, or how much memory we can allocate to each core. This is also done through a calculation, which is also like like Spark basically has its own guidelines that how we should allocate memories. So maybe we can cover that later. But yeah, for now, let's just understand that this executor has in total 5 cores. This core 0, core 1, core 2, core 3, and core 4. So these are the 5 cores which are present. We have 10 gigabytes of RAM for this particular executor. So each core should be getting 2 GB of RAM. So the memory will be allocated evenly across all the cores. So each core will be getting 2 GB of RAM. Now, what will happen is that each core will pick up a partition to process it, right? So we have 5 partitions. So we are having 5 cores. Now each core will pick up one partition and it will process them. Now, if our partitions were uniform, like each partition was of equal size, ideally it is not how exactly Spark works, but let's say we achieve this ideal scenario in which each partition is divided into equal size. So each core will take exactly equal amount of time to process each partition, and they will get us the data all together, right? But in this case, when our partitions are skewed, this core 0 will process this partition, core 1 will process partition P2, core 2 will process partition P3, right? Now, as we can see here, now again, if we let's assume that this is our x-axis, which is the time axis. So as we can see that core 2 will be taking much more time than the other cores to process this particular partition. So this is what data skewness looks like in real time, where one of the partition is taking much more time than the other partitions to get processed. So so now core 2 will be stuck with this partition only. So core 2 has to finish its job to process partition P3, then only it can pick up the next task, right? So this core 2 will be stuck. Now, this is not only about core 2. When this core 2 is processing this partition P3, core 0, core 1, core 3, and core 4, these all four cores will be inoperational. Why? Because they already contain our output for these partitions, which are partition P1, P2, P4, and P5. So they will be containing the output. Now, if we just allocate another task to them, so they will lose their output, right? So these outputs needs to be with these cores until all the core finishes their operations, all the cores finishes processing their data, and finally we have a resultant data at the end. But since this core is still processing its data, so all these cores have to wait for this core to finish, and then only they can pick up the next task. So this is basically our, in simple terms, I can say that this is the wastage of resources. We are having few resources which are just lying over there. We are not using them judiciously. So this basically increases our cost, operation cost, and this is very bad for a company. Okay. Now, so this is what data skewness was, right? Now, data skewness can arise because of various problems. But the first problem, like few of the reasons which comes to my mind right now, the first one could be an aggregation operation. Let's say we have a data and we aggregated the data, like we grouped by, for in this example, we grouped by a certain data on the base of country. And let's say we are having a table in which we are having consumers across different countries, right? So let's say we are having some more consumers from country C4, right? So if we are having more consumers from country C4, so this data will be, and we have partitioned the data based on the country. So this country has the very low consumers. This country has very high consumers. Because of which, while selecting or filtering out data based on this country, the data will be, this partition will be taking much more time as compared to the other countries, because of which data skewness will arise, and it will take a lot more time for this country C4 to filter out the data. So this is the first condition. Because of aggregation, data skewness may arise. The second could be because of joins. So let's say we are having two tables and we are joining these two tables on any join key, and we are having one resultant table. Now, there could be some instances. Let's say we have joined these tables on order line and products. Now there could be few products which were sold much more than the other products. So let's say we have one very popular product which was sold many times than the other products. Because of which, if we filter the data based on this particular product which was sold many times, then we'll be again having data skew, because the partition size will be uneven. Data will be distributed unevenly across all the nodes, leading to data skewness. So this was the introduction to data skewness and few reasons why data skewness may, or how data skewness may arise. Okay. So now let me have a few more images. Okay. So this is one more image which basically represents that how a job is executed in Spark, right? And how data skewness may arise. So let's say we have this one job, right? Now this job will be then broken down into some stages. So this is basically called a lineage graph, which basically is a blueprint on how the job should be executed in Spark. So we have a job, then this job is getting broken up into some stages. Then these stages are broken up into tasks. So now, to get the resultant output, all these tasks needs to be finished. Then only this stage will be finished, and then only this the second stage will start, right? So let's say we have these 4 tasks, and out of these 4 tasks, this third task is taking more time to get complete. Because of which, these three tasks will have to wait. Task 1, task 2, and task 4 will have to wait for the task 3 to finish. Then only they can provide us with a resultant output. Now, so this is what data skewness looks like. There are few disadvantages of data skewness. If we talk about disadvantages of data skewness, the first we can note down could be if a job will be taking more time. So as I mentioned that if we have data skewness, then the job will be taking more time to complete because they have to wait for that particular partition, which is still processing the data, and then only they can present us with the consolidated output. Also, if the job takes more time, it does not it is not only related to job, but it will also take developers time, developers effort to figure out, to troubleshoot that why this job is taking this much time. So all these efforts are go in vain. All these efforts are waste. Second point could be uneven utilization of resources, right? So data skewness can also lead to uneven utilization of resources because, as I mentioned, that in this example, when we had 5 cores, when we have these 5 cores, out of these 5 cores, 1 core was still processing the data, and the rest 4 cores were sitting idle, because of which it led to uneven utilization of resources. Because at the end of the day, we are still paying for those cores because they are active on our account. So when we are paying for those cores and they are not performing anything, then that's just waste of resources, right? So uneven utilization of resources. Also, very important disadvantage, not important, but very deadly disadvantage of data skewness could be data spills. Data spills is regarded as the most, not the most, but one of the most hurtful thing which can happen to data pipelines, because Spark is an in-memory processing engine. Basically, what it does is that it takes the data, it processes the data in memory only. It does not it does not read and write the data again and again to the disk, because it will be a very cost-heavy operation, that writing the data again to the disk and reading it back from there. But in case of data spills, if Spark senses that a data spill is going to happen, what it will do is it will write the data to the disk so that our data remains safe. And when it has overcome that particular situation, it has again freed its resources, it will again fetch the data from the disk. So this writing and fetching the data from the disk, this is not what Spark is meant for, because of which we'll be incurring heavy cost, right? So these are the disadvantages which we can encounter because of data skewness. Now, we have identified the problem. We have learned what the problem is. We have seen that how this problem can arise. We have seen few common disadvantages of this problem. Now, let's talk about few solutions, that how actually we can deal with data skewness. Now, the first solution could be a sorting technique. So here in this image, as we can see, that we have three different data sets. One is for Germany, second is for France, third is for Sweden. So you can think of it as the same, which I was giving the example earlier in the aggregation. So let's say we have data based on data for each country. For Germany, we have these many consumers. From France, we have these many consumers. From Sweden, we have these many consumers. So let's say if I were to filter out consumers who bought a certain product from each country. So now what it will do is it will scan through each country for that particular consumer who bought that particular product, right? So it would be easy for Sweden, right? The data is less, the partition size is less. So it will just scan all the consumers and it will find that, okay, this consumer bought this particular product. For France, it will be comparatively easier. For Germany, it will take more time, like much more time, because it will have to scan this whole partition, which is way much greater in size, and then it will be able to give us the result. Now, what we can do is, in very simple or layman terms, we can just break down this particular partition into more smaller chunks, which are basically comparable to France and Sweden, right? How this is exactly done? So it's a very long technique. We need to have some sorting variable, then we need to combine it with these each partition, and then we have some hash value, and then finally we have these partitions in place. So maybe we can cover that later, but in short, sorting basically means that this bigger partition can be broken down further into some smaller chunks, which are comparable to other partitions as well, because we cannot break it down into more smaller chunks than these. Because let's say if I break it down into one block, so let's say this one block is one partition, second block is another partition, third block is another partition. So then what will happen is that this France data set will be having a data experience problem, right? Because this will be greater than these partitions. So we have to break the bigger partition, but keeping in mind that we also have few partitions. So the size should be comparable between each partition. Okay. I hope this particular technique is clear. Now, the second technique which we can use to handle this data scarce problem is called broadcast variable. Now, for example, let's say we have two tables. One is dimension, another is fact table. So basically, fact table will be always greater than the dimension table. What a fact table, dimension table, maybe if if someone is already familiar with fact and dimension table, or maybe someone is in this course, they must be aware about data modeling and all. So in data modeling, we have this concept called fact and dimension table. So fact table will always be bigger than the dimension table, right? So let's say one table, one table is of size, let's say 2 MB. One table is of only 2 MB in size, and another table is 20 GB in size. Now, if I want to join these two tables, what I will have to do is I will have to shuffle this 2 GB table, sorry, 2 MB table and the 20 GB table across all the clusters, all the cores in the Spark, right? This will be a very heavy operation. Why? Because this 20 GB file, like shuffling this 2 MB file is very easy. This 2 MB file is very small. So shuffling this particular file across the executors or cores is very easy. But shuffling the 20 GB file across these cores will be a very heavy operation, because shuffling this huge amount of data will require a very high cost. So this is not at all recommended. Instead, what we do is we basically broadcast this particular smaller table. So this 2 MB table, we can just broadcast it to all the cores. Let's say we have 3 worker nodes. As we can see over here, we have 3 worker nodes. So what we'll do, we'll take this smaller table, we'll give it to driver, and we'll ask driver that, okay, driver, just broadcast it. By broadcast, we mean that just send the copy of this table to each worker node. So now what will happen? This smaller table will go to worker first. It will search that the table in which I need to join, is it present in worker 1? If it is there, then it will just join over there. If not, then this copy will go to worker 2. It will check over here also that is a table present in which I need to join. If it is present, then it will join, or else it will go to worker 3. And if the table is present, it will getting joined over here. So in this approach, what we did is we just broadcasted this smaller table. So 2 MB, 2 MB, 2 MB, total 6 GB of memory was required to just broadcast this table. And we didn't have to touch the 20 GB table at all. Hence, saving us a very huge cost. And basically, we have avoided the data skewness in this particular situation. Yeah. So this was all about the techniques about data skewness. Right. The third, I do not have the diagram for the third technique, because this third technique was introduced in the recent version of Spark. So this third technique is called adaptive query execution. So basically AQE in short. What this AQE does is, so this is the last solution. So here are the solutions. So first we understood about sorting technique. Second, we saw broadcast joins. Third, now we are discussing about AQE, which is called adaptive query execution, right? So what this AQE does is that it on its own dynamically, it implements sorting technique on our data, and it broadcasts smaller data sets. So let's say if I were to join two data sets, let's say I have data set 1 and I want to join it with data set 2. And if I have enabled this AQE, like this AQE is a property which we need to enable. So if we do AQE as true, then it will do what I'm explaining over here. So let's say we have enabled AQE over here in our Spark environment. Now I'm joining this dataset 1 with this dataset 2. So what AQE will do is it will check that is this dataset is smaller, much more smaller than this particular dataset. If yes, it will automatically broadcast this particular dataset into each node, hence saving us a lot of cost. Let's say when we have joined these datasets, we have a resultant dataset, which is let's call it dataset 3. Now it will check, is the dataset 3 evenly partitioned? Is the data across this particular dataset evenly partitioned across all the nodes? If yes, then okay. If not, then it will basically do sorting on this particular dataset on its own. Apart from this, there are few more advantages of having AQE enabled. Like we can, like it can on its own, it can do coalesce shuffle partition. Coalesce is basically again an optimization technique. If you go into interview, if you prepare for an interview, this is highly asked question. Like 90% of the time, interview the chances are that the interview will ask you difference between coalesce and repartition. So coalesce and repartition are nothing but basically you can increase or decrease the number of partitions. Like let's say, like as I mentioned, coming back to our image. Sorry, coming back to our image. So these are the partitions, right? These 5 partitions: partition P1, P2, P3, P4, and P5. So we can increase or decrease these number of partitions by using 2 techniques. The first one is repartition, second one is coalesce. Like there is a huge difference between both of these techniques, because like there are chances, like because I've seen very experienced data engineers also, they're confused between when to use what, like when to use code for repartition, when to use coalesce. So this is a very tricky question which interviewers might ask you. The second advantage of having AQE, apart from the advantages I mentioned, the first one I mentioned was coalesce, and like it dynamically coalesce the shuffle partition. The second advantage is it dynamically switches the joining strategy. Again, like basically it broadcast joins. Also, if we are joining these 2 data sets, it will decide that what kind of join we should perform, like left join, right join. So it will dynamically switch between the joining strategies, which best suits our requirement. And third one, as we have already discussed, that it will optimize join skews. Basically, it will implement sorting and broadcast joins, and it will optimize join skew. So these were the solutions. To sum it up, data skewness is the uneven distribution of data across partitions in Spark. In Spark, we have different like Spark breaks a particular data into different partitions. If data is unevenly distributed among these partitions, then the chances are that one particular partition will be processed for a very long time, which will lead to some of the resources not being utilized properly. There are disadvantages also for data skewness. Like some few jobs can take more time, which basically means that we'll be having our results later than what we should be having earlier, right? Uneven utilization of resources. We are paying for the resources, but we are not able to use them because of this data skewness problem. Data spills may occur, which is a very, again, cost-heavy operation, right? Then we discussed about the solutions for data skewness. We have following solutions for data skewness. So yeah, that's about that. That's from my side. Let me hand it back to the team. Any questions, guys? I'm open to questions. You can take any questions if you guys have. Not only related to this data skewness, not only related to this optimization technique. Apart from that, if you have any question, like including this data skewness also, or in general for data engineering, for like Azure data engineering, any questions if you have, I'm open to questions.
Yeah. Thank you, Pendra. Thank you. That was a very informative session. So feel free to like ask question, guys, if you have any doubts or if you want to know something in detail. Yeah, I think that's it. Yeah. Thank you again, Upendra, for that informative session. So I hope it will be helpful for all the folks who joined. And yeah, as I mentioned, so feel free to ask any questions or reach out to us if you have any doubts regarding our master data engineering training program. Yeah, please do follow our pages to get more invitations about such a kind of webinars or any courses that we launch. Yep. Thank you guys for joining. Yeah. Bye.
Thank you all. Bye bye.